Hello everybody. Well, we're starting in on week 12 of our lectures. This is our last week, and in fact this is our second last lecture of this course this term. And today we're going to start talking about linear regression. We're going to talk about the theory behind linear regression today, and then our next lecture will be an example to illustrate the sort of things that I'm expecting you to know about linear regression. One of the things we're going to talk about today is the coefficient of, what is it called, determination, which is something that we all need a strong measure of in these last few weeks just to carry on and finish off the term. So keep chin up and carry on. We're soon going to be over. Okay, so for linear regression, I think probably the easiest way is to sort of illustrate this through an example. And my example here is, suppose you're trying to develop a design relationship to predict the flexural strength of fiber-reinforced concrete as a function of fiber content. So some recent bridges in Nova Scotia have been experimenting with this idea of reinforcing the concrete with fibers rather than with steel. This is to avoid corrosion problems because the fiber, of course, doesn't corrode. So, so tests have been done basically to check to see how the flexural strength changes as the fiber content in the concrete increases. And so suppose you've performed a series of such tests and plotted the results, and perhaps you'll see something like this. Flexural strength, which I'll call Y, is the dependent variable on the vertical axis, and on the horizontal axis I've got fiber content, which I'll call X, is the independent variable. So what we're doing is we're varying the content of fiber in the and then checking to see what the resulting flexural strength is. So we think of the fiber content as being non-random. We fix it, and then the flexural strength will be random to some extent, but we'll show a linear, some sort of dependence on the fiber content. And so the idea here is to come up with a line of best fit that we can use in a design context. So suppose we wanted to establish that design relationship between X and Y, then basically we're looking for a line of what I'm calling best in quotes fit, but the problem is, how do we define best? There's probably many different possibilities, but I just sort of dreamed up a couple. One that doesn't make much sense and one that does make sense. So the first one is the one that doesn't make a whole lot of sense, but we could define best as the line that passes through the most points. So for example, if we saw something like this, then this red line is probably the best because it passes through 3 points, and I don't think I can find any other combination of points where we can pass through more than 3 points. But we can see that red line is really not a very good prediction of what's going on with all of these points. The line should actually be more along this sort of direction. And all the other lines that I'm coming up with are just through 2 points, and none of them are very good either. So none of this particular definition of best is not really a very good definition. The definition that we end up using in practice is the line that minimizes the errors between the observations and the predictions. And this is a good approach. We'll illustrate this with a simple case. Let's suppose that our random variable y, which is a thing we're trying to predict, is a linear combination of the x values plus a random error. So it's an intercept plus a slope times x plus some sort of random error. And that random error just reflects the fact that y is not completely predicted by x. There are other things that influence the value of y that we don't know about, and therefore it's random. But in a linear regression approach, we assume that this random error is normally distributed with mean zero and variance sigma squared, and we make this assumption so that we can do things like establish confidence intervals on y and on the parameters beta naught and beta 1. So the normal distribution is a requirement. Mean zero and variance has to be constant. Actually, there's a more general linear regression approach where variance is not necessarily constant, but we're not going to consider that in this course. If I take the expectation of this line, equation 1, I see the expected value of y given a particular value of x is just, if this thing is mean zero, it disappears. So the expected value of y is just, given x, is just beta naught plus beta 1x. And so basically our line of best fit is the expected or the mean of y as a function of x. And so our task here is to find beta naught and beta 1. Once we have obtained a set of observations, then equation 1, which is this random form up here, becomes a lowercase form. We have the x's in both cases are fixed, so they are non-random, but the y has this random component. And what happens is that random component now becomes an observed, what we call a residual, so an observed error. And the y becomes an observation, so this is lowercase as well. So we get an expression now between our observed values of y, beta naught, beta 1, at each point xi, and some residual error. The picture is looking like this now. If I've got this first observation y1, the height of this point here is y1. The prediction is the red line. It's given by this prediction equation, y equals beta naught plus beta 1x. And we've got an error between our prediction and our observation, and that's E1. And in more generally speaking, EI is the error between the ith prediction observation point and our prediction point. So this is the ith value of yi is this height here at the location xi, and there's an error EI there. In fact, we can rearrange this formula here and solve for the EI, and it's just equal to yi minus our prediction at the point xi. More generally, if our prediction is more complicated, we could just write this part as the y, the predicted value of y at the ith location, and I call that yi comma predicted. We're not going to really talk about this very much longer. We basically just look at this particular definition of EI in this course, but we could have a more general formulation, and we'll see a little bit of that coming up. Okay, so now the task is to minimize some function of these residuals, so some function of these errors. So I'm going to write the errors as a vector, and then I denote a vector with a little squiggle underneath the E. And this is this is a row vector in this case, the vector of the errors between the first observation point and the prediction, and so on and so forth up to the nth. So I'm assuming that I've got n observations here. And we want to minimize some function of these residuals. As soon as I see the words minimize some function, I'm thinking taking derivatives and setting them equal to 0. So let's see how we go about doing that. Some possibilities then are to minimize, so the question is, what function should we be minimizing here? We could try minimizing the sum of the EIs. The problem with that, of course, is that the minimum of E is minus infinity. So basically the minimization of this sum means all the E's go to minus infinity, and this line of best fit just drops off down to minus infinity, and it's of no use to us. So this is not an option here. What we have to do is get rid of the sign. So another option is to minimize the sum of the absolute values of the I's. This is actually a good approach, but the problem is that the derivative is undefined at the minimum of the absolute value. If you think about the shape of y equals absolute value of x, it's that familiar V shape. But this thing, the derivative on this side is -1, and on this side is +1. It is never equal to 0. At this point here, it just passes from -1 to +1 and is not actually equal to 0. So mathematically, this is hard to find the point of minimum point of the absolute value. We know we can see it here, but when we have higher dimensions and we're talking about a bunch of E's, it becomes more complicated. So it's nicer if we can actually define where the 0 point is in the derivative. So basically, to get rid of the sign, the thing we do is we square the EI's. So that gets rid of the sign, and the big advantage to this is that the derivative of this is continuous and basically is equal to 0 when we hit the minimum. So we're going to define a quantity called SSE, and this is called the sum of squared errors. So that's where the SSE comes from. And basically, this is just equal to this sum of the EI squared. And in writing it out, each EI is yi minus its prediction, which is beta naught plus beta 1 xi, and then we're squaring the whole quantity. And the task now is to find the values of beta naught and beta 1, which minimize this function, SSE. with respect to those two values, beta naught and beta 1. And the really nice thing about this statement here is that it leads to two equations and two unknowns. All we have to do is take the derivative of SSE with respect to beta naught and set that equal to 0. That's one equation. And then the derivative of SSE with respect to beta 1 and set that equal to 0. That gives us our second equation. We know we have two unknowns. Now we've got two equations. We can solve for those unknowns. Okay, so if we actually take the derivative with respect to beta naught of this quantity up here, the 2 comes down out front. There's a minus sign in front of the beta naught, so there's a minus 1 also in the derivative, and then we're left with what's inside the brackets here. So we got minus 2 sum I equals 1 to n of yi minus its prediction, and we set that whole thing equal to 0. The derivative with respect to beta 1, the 2 comes down in front again, and we've got a beta 1 times minus xi. So there's a minus xi coefficient here that comes in here. So we got minus 2xi, and then the contents of the square brackets again in here. And we set this equal to 0. Okay, so there's our two equations. Well, we see automatically if this thing here is equal to 0 and this thing is equal to 0, we can first of all divide through by minus 2 and get rid of that term. Before I do that, I just wanted to mention that this approach, this idea of taking derivatives and setting them equal to 0 is easily extended to higher order lines of best fit. So suppose we had yi was a quadratic function of x. So beta naught plus beta 1 xi plus beta 2 xi squared plus some error. Now I can fit a curve to my data, and all I have to do is define SSE as the yi minus its prediction, this part of it here, and then differentiate the SSE with respect to the three unknown parameters, beta naught, beta 1, beta 2, and this gives us three equations and three unknowns. Okay, so basically we can extend this to any polynomial function of xi. Okay, and in fact any function of xi. The main thing is that the parameters beta naught, beta 1, beta 2 have to appear linearly. Okay, so they cannot appear non-linearly. That's why it's called linear regression. It's not that we're fitting a straight line, but that those parameters, beta naught, beta 1, beta 2, and so on and so forth, appear linearly in the prediction equation. But the x's don't have to appear linear. We could have cos x here and tan x here, for example. Anyhow, let's get back to our simple problem where we're trying to fit a straight line. We have these two derivatives up here. We first of all divide through by minus 2, and that gets rid of the minus 2 up front, and I'm left with these two equations. Now I'm going to just propagate the sums through each of these equations. So I've got the sum I equals 1 to n of yi minus the sum I equals 1 to n of beta naught minus the sum I equals 1 to n of beta 1 xi, and similarly for the second equation. So I see these sums coming up here. First of all, the sum of beta naught I equals 1 to n is just beta naught plus beta naught plus beta naught n times. So this is, of course, just n times beta naught. The beta 1 here can come out front of this sum. What else? We got another constant here. This can come out in front of this sum, and the beta 1 can come out front here. And I'm left then with these terms here. So sum of yi's minus n beta naught minus beta 1, sum of the xi's, and similarly for the second equation. Okay, so the next thing we're going to do is going to move the non-beta terms to the right-hand side. So this term here doesn't involve beta, either beta naught or beta 1. So I'm going to put this on this side. That becomes minus I equals 1 to n of yi. And this one here doesn't involve beta, so I'll put it on this side. It becomes minus xi, sum of xi yi. Now there's a whole pile of minus signs in here. I'm just going to multiply everything through by minus 1 on both sides, and that gets rid of all the minus signs. And I'm left with two equations that look like this. N times beta naught plus the sum of xi's times beta 1 equals the sum of yi's. Sum of xi's times beta naught plus the sum of xi squared times beta 1 is equal to the sum of xi yi's. And in fact, I can write this now as a matrix equation. So I just have beta naught and beta 1 as a column vector. This is my matrix of coefficients that I multiply this by, and this is my right-hand side vector. So to solve this matrix equation, we just need to compute a series of sums. We see a sum of xi's here and here. sum of xi squareds here, sum of yi's, and sum of xi yi's. It turns out that there's one more sum that we need, and that turns out to be the fourth one here, the sum of the yi squared. So that's not actually needed to solve this system of equations, but we'll need this to evaluate variability of our variability and confidence intervals hypothesis tests of the linear regression. So we will need altogether 5 sums at the end. Sum of the xi's, this leads to x bar is equal to 1 over n times the sum of xi's. Sum of the yi's, and by the way, sum of the xi's appears here, and sum of yi's appear here. So the sum of the yi's gives us y bar is 1 over n times this sum. By the way, I've dropped the y equals 1 to n on all of these sums. It's understood that all of these sums are summed over all n values. Sum of the xi squareds is up in here, leads to something we're going to call SS sub xx. And this is the sum of the square deviations between the x values and their average. And we can write that as the sum of xi squared, which is the sum we're coming up with here, minus n times x bar squared, which was this quantity up here. Sum of yi squareds leads to something we're going to call SS sub yy. And that's just the sum of the square deviations between yi and y bar. And we can write that as the sum of the yi squareds, which is that sum we're coming up with here, minus n times y bar squared, which we got up here. And finally, we got the cross term, the sum of xi times yi, and this leads to something that we call SS sub xy. And we'll see here, this is really a sort of an estimate of the covariance. And it's the sum of xi minus x bar times yi minus y bar. And we can write that as the sum of xi yi, which is the sum we're coming up with here, minus n times x bar y bar. Okay, so basically our task in the regression so far is just to come up with these 5 sums. After you've done that, all of these equations here are given to you in the summary pages, and you can use them to find these quantities. And from there we can get everything we need to perform a linear regression. We can compute the various quantities that we're after. SSE was the sum of squared errors, which we had up here somewhere. This guy here is the SSE is the sum of the squared errors between our observations and our predictions. And SSE now can be obtained directly from these things that we've computed up here, SSYY. That was the one that we needed here to find this SSE, minus SSXY squared over SSXX. Perhaps the most interesting rate at the moment is that our line of best fit can now be estimated directly from these quantities that we've computed up here. Beta 1 hat, which is the slope. And by the way, I'm putting a hat on this now because this is an estimate of the slope. We don't actually know the true slope between x and y until n goes to infinity. So this is just like x bar. The bar is indicating that it's an estimate, and in fact that estimate is random. If I take another set of observations, I'm going to get a different beta 1 hat. Okay, so the hat is just emphasizing that this is an estimate. Is SSXY divided by SSXX. And then the other thing that we need to note is that our line of best fit passes through the average point, x bar, y bar. So every line that we best fit line that we come up with will pass through this x bar, y bar, and that allows us to easily compute beta naught hat is y bar minus beta 1 hat over x bar. So I find this first and then plug it into a relationship that insists that we're passing through x bar, y bar. Once we have that, then we can write out our line of best fit is just y is equal to beta naught hat plus beta 1 hat times x. Okay, so that becomes our line of best fit. Okay, now that prediction line that we've just written up there has errors between it and the true values of y, and the estimate of the variance of those error residuals we're calling sigma squared over here, And the estimate of that variance is s squared, and it's basically 1 over n minus 2 times the sum of the square deviations between our y's and their prediction. Now this prediction involves two parameters that we've estimated, beta naught hat and beta 1 hat, and that's why we lose 2 degrees of freedom here. So it's 1 over n minus 2. Another way of writing this s squared is SSE divided by n minus 2, because this sum here is just SSE. So we lose 2 degrees freedom due to the estimating beta naught and beta 1. Okay, so this thing here is going to be, when we standardize it, is going to be chi-squared distributed. The next question is how good is our fit to the data, to our observations? And for this, we're going to define r squared to be the coefficient of determination, the thing that I mentioned earlier in this lecture. It's basically a measure of how well our line fits the observations. And you'll see in the summary pages again an expression for r squared. I think the summary page has this version here, SSYY minus SSE divided by SSYY. Of course, these two things are the same, so another way of expressing this is 1 minus SSE over SSYY. I wasn't sure which is the easiest one to put in the summary pages. I just put this one in the summary pages. We have to compute all of these quantities anyhow in order to find this. Perhaps the thing to remember that r squared is actually an estimate of rho squared. If you recall, rho is the correlation coefficient between x and y, and it lies between minus 1 and plus 1, and so its square lies between 0 and 1. And basically then r squared tells me how well I'm fitting the data. So if r squared is close to 1, then we have strong agreement between our fitted line and our observations. And basically, if r squared is very close to 1, I would see something like this. So my points maybe are showing a little bit of variability, but they're pretty close to the line. And so I've just said this is r squared of 0.98. If we've got lots of scatter, but still some vague trend, our r squared is going to be lower. I put here r squared is 0.2. And just as we had for the correlation coefficient, even if the line is close to the observations, but if it's flat, that means that the line of best fit is a constant which is independent of x. And if it's independent of x, then our correlation coefficient is 0, and that also means r squared is 0. So r squared isn't just telling us how close we are to the points, it also tells us how linearly dependent x and y are. And if they're not, then this becomes 0. Okay, so as I mentioned, the estimators beta naught and beta 1 hat are actually random. They change if I collect another set of observations, just like x bar in previous chapters. So, for example, if I've got a set of these blue observations here, my line of best fit might be this red line here. But if I went out and did the test again and took another set of observations, I might get the green points here. And my line of best fit then might be this green line here. And if I keep repeating this, I'm going to get a bunch of lines and different orientations. They are all going to pass through the average. The average is changing a little bit as well every time I take another set of data. But averages change less than the data itself because averages have a smaller variance, a smaller standard deviation. They're divided by square root of n. So basically we'll get these lines are more clustered or more centered here, but as we get farther and farther away from the average location, the slopes start to cause them to get farther and farther apart. So the confidence interval on the line of best fit has this sort of curved shape, and that's what these black lines are showing is the confidence interval on my line of best fit. It's the smallest confidence rate near the middle here, and less confidence as we go farther and farther away from the middle. We're not going to talk about the confidence interval on the line of best fit, but we will talk about confidence intervals on the parameters of that line. And so let's talk first of all about the variability of the slope, which is beta 1 hat. We can show that the expected value of beta 1 hat is just equal to the true beta 1, and so the estimator that we're using here is unbiased. We can also show that the variance of beta 1 hat is equal to sigma squared over the sum of the square deviations between xi and x bar. And that thing down here is just SSXX. This thing up here is estimated by s squared. So the estimate of the variance of beta 1 hat is s squared over ssxx. And we can write this also as SSE over n minus 2 SSXX. And I've forgotten which one I actually put in the summary pages. S beta. Okay, so I put this one in the summary pages. Okay, so it actually, as long as we've computed s squared first of all, then it's easy to compute this. If we haven't, then just use this version here. But the computation of s squared is also in the summary pages and is up here as SSE over n minus 2. Okay, so that's the sample variance of beta 1 hat. Once we have that, we can now develop confidence intervals and perform hypothesis tests on beta 1. For example, a confidence interval on beta 1 is the usual LU equals something plus or minus something times something. We don't know the true variance, so we're going to use T here. This is a two-sided confidence interval, so this will be alpha by 2. The computation of the sample variance involves a denominator of n minus 2, so we lose 2 degrees of freedom. So the number of degrees of freedom here is n minus 2. And then we just have to figure out what to put in the rest of the somethings. This is a confidence interval on beta 1, so this is its estimate, which is beta 1 hat. And this is just the standard deviation of that estimate. And we've just computed that, the variance of that up here. So it's going to be the square root of s squared over SSXX. So there's the confidence interval. It's very similar if we're doing a hypothesis test. Sometimes we want to test to see whether beta 1 is different than 0. Because if beta 1 is 0, then it means x and y are independent. The other thing we can look at is the variability of the intercept, or beta naught hat. We can again show the expected value of beta naught hat is just beta naught, and so this is unbiased. The variance of beta naught hat is, we can show that's equal to sigma squared times the sum of the xi squareds over n times the sum of xi minus x bar squared. The sample variance is basically an estimate of this thing here. We do some manipulations and throw in our various SS's, and it turns out that that sample variance is just s squared times 1 over n plus x bar squared over SSXX. So basically a confidence interval on beta naught then becomes their usual LU equals something plus or minus something times something. This thing here is going to be T again because we don't know the true standard deviation, alpha by 2 because it's a two-sided confidence interval, and n minus 2 degrees of freedom. And then the first something, if it's a confidence interval on the true intercept, is its estimate, which is beta naught hat. And then we put the standard deviation of beta naught hat in here, and that's what we just computed here, or the variance here. We just have to put the square root in here. Okay, well that concludes the theory that we're going to discuss in linear regression. So the next lecture we'll be looking at an example of this, and then we're done. There'll be tests in a couple of weeks on this, and then the course is over. Okay, so I'll sign off there, and I'll talk to you in the next lecture.